Europe's biggest engineering project is a high-speed railway that will stretch from London to Birmingham in the UK, and it has a lot of tunnels. They're being built by these gigantic machines that span over 170 metres long and weigh more than 2,000 tonnes. That's longer than 16 buses and the weight of more than 300 elephants. They are seriously big. But where did we get the idea from to tunnel like this? And how transformational has that idea been? The answer is something properly wow. We're on our way to one of High Speed 2's tunnel portals in West London to see one of these giant machines. The tunnel boring machines, or TBMs as they're known, are tunnelling 24 hours a day. There are around 65 miles of tunnels on HS2, and when engineers have dug all those tunnels, 130 million tonnes of earth will have been dug out. That's enough to fill Wembley Stadium 15 times. This is the Victoria Road crossover box where TBMs Emily and Dan were launched from. It's shaped kind of like a caterpillar with 5 bubbles, and it was the first of its kind in the UK designed this way to save concrete. It's a gigantic structure. There's enough space in here to hold 800,000 bathtubs of water. 2 tunnel bores come out of each end of the caterpillar, one set heading towards London and the other set heading towards Birmingham. When HS2 is finished, trains will be able to cross over from one tunnel to another in this box. It's going to be left open to the air to provide ventilation and an emergency access route. But for now, it's a major construction site, and they've let me in to have a look around. But whoa, hang on, we need to take a step back on this journey. Because the crazy part about these huge machines is that the idea from them came from something really, really small that we discovered a really long time ago. Back in 1502, the famous explorer Christopher Columbus was stranded in Jamaica for over a year when his ship was eaten by the enemy most feared by sailors. Not the mythical Kraken or some hungry pirates, by a creature that is deadly to wooden ships and apparently sank more of them than enemy cannon fire did. A worm. It wasn't actually a worm at all, but that's what Columbus described it as because its long body made it look like a worm. It was in fact a bivalve, a clam that lives outside of its shell. And that's the inspirational thing about these creatures for tunnelling, their shell. This is Reuben Shipway. Reuben has been studying shipworms for over 15 years, and he still hasn't figured out everything there is to know about them. So how do shipworms tunnel then?
Their superpower for tunnelling through wood basically comes from this amazing shell that they've evolved. So if we look at the shell under really high-powered microscopy, we see that it's covered in thousands and thousands of tiny teeth.
And so how do they keep their tunnels from collapsing around them?
As they continue to tunnel and bore into the wood, they're continually eating the wood, and their body lengthens because they basically have to get to the next piece of wood and the next piece of wood and the next piece of wood. So they're continually lengthening the burrow. And as they lengthen, what they do is they lay down this calcium carbonate white tube along their body.
So how successful are shipworms at tunnelling then?
Oh, it's absolutely their superpower. They are, I would say, probably the most successful tunnelling animals on the planet.
3 centuries after Columbus was shipwrecked by the shipworm, its incredible ability to tunnel without collapse became the inspiration for the grandfather of tunnelling. Marc Brunel was a civil engineer in the 1800s, but engineer doesn't really do him justice. He was a visionary. Where others saw problems, he saw only solutions. And he was determined to make the impossible possible. He wanted to do something nobody had done before. London desperately needed a way to cross the River Thames, but every tunnel that was started flooded or collapsed. Many people said that it just couldn't be done, but Marc didn't give up. While he was working at a dockyard, he found a piece of wood that had been removed from the keel of a ship, and it was riddled with all these little holes and tunnels that were made by Teredo nivalis, the shipworm. He decided that if these little things could build tunnels that didn't collapse, so could he, and he set about building the tunnel shield. And this is what he built with it. You can't actually see it because it's under the water. The Thames Tunnel is under the river just here.
Today, it's part of the London Overground network on the Windrush line.
And it's one of the most important pieces of tunnelling history because it was the first tunnel built under a navigable river. And it's the beginning of the story for all our really big tunnels. This is the Brunel Museum, which tells the story not just of Marc, but of his whole incredible family, because Marc was the father of better-known Isambard Kingdom Brunel, who built ships, railways, hospitals, countless feats of engineering. And this is the tunnel shaft that Marc Brunel started the Thames Tunnel from.
This is Catherine McAlpine, director of the Brunel Museum and all-round expert on Marc's tunnelling triumph.
So we're here in the tunnel shaft, which might seem like just a great big hole in the ground, but actually it's quite a special big hole in the ground. At the time it was constructed, it was actually the biggest example of what's known as the caisson method. So what that is it's two big sort of iron hoops, one at the bottom, one at the top, connected by sort of brick walls connecting the two of them. And then they're constructed on the top of the ground, and then using gravity and the soft earth here at Rotherhithe, they just sink into the ground, and they kind of put the bricks, 50 tons worth of weight sort of up on the top to allow it to sink into the earth. And then once it's sunk, it allows you access underneath the river to start digging your tunnel. And that's what Marc Brunel was able to do using his patented tunnelling shield.
The tunnelling shield was an ingenious way of digging under a river. A protective wooden layer over the top of the shield would keep the miners underneath it safe from collapse from the ground above. There were 3 layers of 12 cells, each with a miner inside. The miners would remove a wooden board from in front of them, dig about half the size of a brick ahead, and then the whole structure would move forward. All the time being followed by bricklayers lining the tunnel, just as the Shipworm does with its calcium carbonate tube.
This was the model that was owned by Marc Brunel himself, and we have it here as part of our collection at the Brunel Museum, but we've actually never had it on display before.
Wow, so this was actually Marc Brunel's model?
Yeah, it was absolutely his.
Marc's eventual success with the Thames Tunnel was the beginning of a tunnelling revolution. Just a year after the Thames Tunnel opened, a man was born who would eventually go on to develop Marc Brunel's tunnel shield into an even better design that would eventually be used to dig most of the running tunnels for the London Underground.
Here he is, James Henry Greathead. He developed a concept that an engineer called William Barlow came up with in 1862, a circular shield that would work through clay, a bit like an apple corer. His was the first cylindrical tunnelling shield, but it worked on the same principle of miners excavating the earth while protected by the shield, which would move forward as each section was dug. Greathead used this shield to dig the world's very first tube tunnel, the Tower Subway, which opened in 1870. It was only just over 2 metres wide, and just like Brunel's tunnel, it went under the Thames.
This brick drum near the Tower of London is the only remnant we can still see, and it's not even original. It was built in the 1920s as a replacement entrance to the tunnel. But how amazing is it that people pass by here every day and they have no idea that they're passing by the entrance to an abandoned tunnel under the Thames?
It wasn't very successful as a railway tunnel and was taken over within months by the London Hydraulic Power Company. Now it carries water mains and telecommunications cables.
We've been improving on that tunnelling machine design continuously and had countless successes with what is fundamentally the same principle.
By the time the Victoria line was dug in the 1960s, it was over 50 years since the last new line, and Greathead's design had been improved again to incorporate much more effective rotary cutters. And the use of precast concrete segments replaced the traditional cast iron rings of the past.
We've gone on to use this continuously improving design to dig the Channel Tunnel between England and France, and more recently on Crossrail, the Elizabeth Line, the UK's busiest railway.
And that brings us back to the tunnels being built right now under London for HS2, using just the same ideas as Marc Brunel and James Henry Greathead, just on a much bigger scale.
Up those stairs there.
This one here, yeah?
So about halfway between the back of the machine and the front. This is the MSV loaded with all the tunnel rings. So this is what the tunnel is built of, these.
And how much do each of these weigh?
12 ton?
12 tons
Something like that,
each
yeah.
way.
I'm not entirely sure of the weight, but it's a massive lump of reinforced concrete.
They are huge.
I suppose the point to make, if you haven't realised, is everything here is moving. As I said before, we're not mining at the moment, but the only thing that doesn't move is that piece of concrete. So if you were stood here leaning against that piece of concrete, eventually that would touch you, because this whole process moves. When we start to mine, which we will do shortly, they've just finished building. As you can hear that rattling noise a minute ago, that was them bolting the rings together. So that means we're about to start mining, I think. So the next stage of the process, the individual segments have been unloaded from the MSV and they're on this little transfer car. And then they get lifted up by this crane, which is a vacuum crane. So there's no lifting point as such.
So it's lifting it by sucking it up, basically.
Brings it to here, spins it through 90 degrees and drops it down here. And then again, as the rings are built, this machine advances, taking the segments in one by one, and then the erector arm lifts them up, which you'll see in a minute. This is the conveyor belt coming up from...
So is this where all the spoil's going? Oh,
Yeah,
you can
so
see
it comes-
it. Yeah,
comes out the middle of the head,
yeah,
which you'll see in a minute, in a screw conveyor.
yeah.
And then it transfers onto a rubber conveyor, and that goes all the way out. And the amazing thing about this is it's one conveyor belt all the way down the tunnel, all the way out the shaft, all the way into the Flatiron site on the other side of the road from where we were based.
One
conveyor belt, yeah. So we're mining at the moment. That's the spoil coming out of the head of the machine. We take one walk back there while they're mining, and then when they finish, we'll go up the front and watch the ring build.
That's inside the cutter head there. That's basically then the foam system. So we're injecting foam, water and air to condition them up when we're mining. These are all our pressures. So we have to keep a certain pressure when we're mining. That's basically our guidance system then.
Oh, so you can actually steer it from here and just press the buttons to get it into the right place.
Yeah, so basically press stop there. That shoves it left, that shoves it right, that shoves it up, that shoves it down.
It's fairly simple.
Yeah, it's not too bad, yeah.
That instrument there is the guidance system.
Oh, what, the laser?
So there's a theodolite there with a laser. The laser hits a target on the machine, and as long as you know where either end of that point is, you can work out where the machine is. We'll go and have a look at the front now, because we should be just about to start building.
Exciting.
Hello, mate. Right, so this is the bit that does all the work. The cutting head is behind those motors. Those are the motors that drive the machine. Behind you is the erector arm, which they've just fired up, so now about to build the ring. You can see the machine has shoved the last ring 1.9 meters away from where we were.
Yeah.
Individually, they retract a number of rings, pick a segment up from the invert, spin it around, put it into place, bolt it to the previous ring, and then held in place with the rams. And then they do that 6 times, and you've built another 1.9 meters of tunnel. Right, our chariot awaits, so we'll walk back.
Tunnel boring machines have allowed us to think big about tunnels and to travel under rivers and under cities in a way that just wouldn't have been possible otherwise. If Marc Brunel had never seen the work of the Shipworm, he might never have successfully tunnelled under the Thames. The Great Head Shield might never have been developed, and the deep tube lines under London might never have been dug. The inspiration of a clam gave tunnelling to the world, and there is still so much more we might be able to learn from them.
If we just look at the biomimicry, for example, just the adaptations of the animal, and then we try and apply that, we've got all these other different species that have these different shapes of shell. Perhaps we can improve different tunneling devices based on those different shapes of shell. One of the beautiful things about science is that the more you discover, the more questions reveal later on down the line. I don't think we'll ever completely solve the mystery of the Shipworm. There will be more and more questions, more and more discoveries, and lots of things to learn.
Just imagine what Brunel would think if he could see what we've built with his moment of genius witnessing the work of a shipworm. I'm pretty sure he'd say, wow. If you've enjoyed being wowed, subscribe to the channel to help us create even bigger wow moments.